So example 3 now, using the box plot fences and the normal distribution. So we're looking to see what are the relationships between the features of a box plot and the normal distribution. So a quick review of the fact that the upper and lower fences of a box plot, the upper and lower fences require us to write down the quartiles, and the lower fence is quartile 1 minus 1.5 times the interquartile range. The upper fence is quartile 3 plus 1.5 times the interquartile range. So those are the ways we're going to calculate our fences. And we're asked to use this probability to explain why the fences are useful for highlighting possible outliers. So to go into the calculations for those fences, the first thing we need to do is to write down, remember that the lower fence is lower quartile minus 1.5 times the interquartile range, upper fence is upper quartile plus 1.5 times the interquartile range. So that's how we're going to calculate those values. So in order to find the Z value for the quartiles, that's our first problem. So we need to find quartile 1, which means the point which is 1/4 of the way up the distribution. So showing our normal distribution with a mean of 0, this is the Z-score, what we're looking for is the area up to quartile 1 is 1/4 of the whole, which is 0.25. Remember, the whole is 1, the area under that graph is 1, so we need quartile 1, the Z-score, such that the area up to that point is 0.25. And we'll get that by using, in Excel, norm S, INV. So norm S, INV, and 0.25. So from Excel, we can go into Excel just to show you where that's coming from. And again, using the function here, norm S, INV, all we need to put into there is the probability. The probability we have here is 0.25. And when we put 0.25 in there, we get negative 0.674. So we'll use 0.6745, negative 0.6475. And clearly, when we look for the third upper quartile, quartile 3, what we're looking for there is similarly the position in the Z distribution on the right-hand side, such that 3/4 or 0.75 is the area up to that point. So this time we're looking for 3/4 or 0.75 for the probability. Of course, we don't need to do any further working here. We can use norm SINV and 0.75, but because this is a symmetrical distribution with 0 in the middle, very clearly you can see that that will also be 0.6745. The same value, but without the negative sign, as we had for quartile 1. So now we have our upper and lower quartiles, and we can calculate the interquartile range. Interquartile range is calculated by subtracting the lower quartile from the upper quartile. So now we have those figures, we can work out the interquartile range, quartile 3 minus quartile 1, 0.6745 minus negative 0.6745, and that comes out at 1.349. So at the interquartile range, 1.349. Now, of course, we need to multiply that by 1.5, so 1.5 times the interquartile range, in order to add that to the fences. So our fences, the lower fence, quartile 1 minus 1.5 times the interquartile range. We have quartile 1, that's negative 0.6745, minus 1.5 multiplied by 1.349, and that comes out to be negative 2.68. And again, clearly, the upper fence is going to be quartile 3 plus 1.5 times the interquartile range, and those values will be the same but positive 0.6745 plus 1.5 times the interquartile range, and that will give us positive 2.68. So in order to calculate the probability that an observation lies between the upper and lower fences, we need to find the probability that Z lies between negative 2.68 and positive 2.68. And again, if we draw a diagram for that, we're looking for the probability of lying between those 2 points, 0 in the middle, 2.68 on the right-hand side, and negative 2.68 symmetrically placed on the right-hand side. And remember that Z distribution, as we've seen it before, we very rarely see values that are bigger than 3 on either side. So again here, to calculate this probability, as we did in the previous example, we're going to use norm S dist this time, because this is a standard normal, so we can use norm S dist of 2.68 minus norm S dist of negative 2.68. And the values given there from Excel are 0.9963, take away 0.0037, and that gives us a probability of 0.9926, or in fact 99.26% of the entire distribution lies between those two values. And clearly this is defining for us, beyond those points, very unusual values which we do think of and call outliers. So that's the end of example 3.